The experiments of Faraday and Henry. When electricity and magnetism are studied together, the effect of changing magnetic field is very important. Michael Faraday and Joseph Henry, in the year 1831, independently proved that electromotive force gets induced in a closed circuit due to changing magnetic field. Electromotive force or current also gets induced when a closed loop of wire or conductor is moved under the influence of magnetic field. Faraday and Henry performed lots of experiments to learn about the connection between electricity and magnetism. The results of these experiments have led to the lifestyles of today's men who made life easy by using lots of electrical applications. Some of the experiments are as follows. Experiment number 1. The apparatus of this experiment consists of a coil, a galvanometer, and a strong bar magnet. It is observed that when the bar magnet is stationary, the galvanometer shows no deflection. When the north pole of bar magnet is moved towards the coil, galvanometer shows deflection in one direction. It indicates the flow of current through the coil. When the bar magnet is moved away from the coil, galvanometer again shows deflection, but now in opposite direction. Thus, it again indicates the flow of current through the coil. It is found that the deflection of galvanometer is more if the bar magnet is moved rapidly towards or away from the coil. Thus, it can be concluded that whenever there is relative motion between a coil and the magnet, induced current flows through the coil. If the relative motion between the coil and magnet is large, then large EMF and current are produced in the coil. Experiment 2. If a second coil Y carrying a steady current drawn from a battery is moved towards the coil X connected to a galvanometer, then the galvanometer shows a deflection. This confirms that an electric 2 current is induced in coil X. The deflection in the galvanometer lasts as long as the coil Y is in motion. When coil Y is moved away from the coil X, the galvanometer shows a deflection in the opposite direction. It is also noted that the deflection lasts as long as the coil Y is in motion. No deflection is shown by the galvanometer when the coil Y is stationary. Now, if the coil X is moved towards or away from the stationary coil Y, the same results are produced. It establishes that electric current in the coil X is induced due to the relative motion between the two coils. It does not matter which is moving. In both the cases, the deflection and consequently current becomes larger if a coil is moved towards or away from the other coil at a quicker rate. Experiment 3. Is relative motion between a magnet and a coil, Experiment 1, and between two coils, Experiment 2, is necessary to induce current? Faraday answered this question through another experiment and concluded that the relative motion is not an absolute requirement. Both the coils P and S are fixed. Coil S is connected to galvanometer, while the coil P is connected through a tapping key K. Coil P is generally called primary coil and coil S is called secondary coil. A momentary deflection is observed in the galvanometer when the tapping key K is pressed. The deflection shown by the galvanometer becomes zero almost instantly even if the key is kept pressed to maintain current in the primary coil P. Now, if the key is released, a momentary deflection is again observed, but in the opposite direction. Clearly, the deflection in the galvanometer is produced only when the key is pressed or released in the primary coil or circuit or winding. It was concluded that the factor responsible for inducing current in the secondary coil, and hence the deflection in the galvanometer, is the change in magnetic flux due to change in current in the primary coil. It is also observed that the deflection increases when an iron rod is inserted into the coils along their axis.